So, the summary is fairly short, right? And this is essentially kind of what you get from a standard book like Ross, right? So, in terms of reversibility, mostly what's discussed is just, just the definition, right? And I'll read it from the board, and we'll discuss how it's not different, it's just slightly more general, but very related to what we saw in lecture. So, a Markov chain is called reversible, time reversible, if its stationary distribution pi satisfies the local balance equations, right, which are right here, and they have to hold for all pairs of states x, y. So the only difference in this kind of standard textbook definition is that pi x is allowed to be 0, right? We didn't, because in our construction of this time reflected process x prime, right, the time reverse chain, we had to divide by pi x, and so it had to be 0. So if you look, it had to be greater than 0. And so if you're looking for kind of an extra challenge, you can try to see how do you reconcile kind of the theory that I presented with the sort of well-motivated definitions of reversibility, being that a process is reversible when it's equal to its time reverse chain. How do you kind of adjust or patch that theory when something like this happens, right, when pi x is equal to 0? And I think some of the examples in the upcoming lecture will also kind of help you get a sense about what this really means, and on an intuitive sense, and also mathematically. But for the sake of sort of having a kind of the most general definition to work with, this is the one you want to go with, and it is perfectly okay for pi x to be equal to 0. I'll mention another quick thing. If you were to replace the pi with a mu, the stationary measure, generally that one would call mu a reversible measure. So you sometimes see kind of that definition in advanced books. But kind of as a word of caution, you'll note that in lemma 3, right, we had to start the chain x and its time reverse chain x prime from the stationary distribution pi. And if you try to do the same for a stationary measure, whether it's reversible or not, you're not necessarily going to be able to do this, because it's a stationary measure is not always a distribution. And so we'll be more to say about this when we get to the lecture, when we look at cases where the stationary measure exists but the stationary distribution does not. And as a final thing, and this is a bit of a challenge problem, but also something good to know about, it's so the things below this line is not related to reversibility at all in any kind of strict sense. So here I'm just looking at a condition. Hopefully you recognize this as the Markov property, right? This is what defines a Markov chain, right? Namely that the process at some time condition on the previous path only depends on sort of the most recent kind of point in time, right? That maybe the present state, if you think of time k as the present. What's not often mentioned is that this Markov property, and again, whether this is reversible, x here can be reversible or not. That's not the issue, right? So x may be reversible, x may not be reversible. The point is, if it has a Markov property, it also has the same Markov property looking forward in time, right? So this is kind of related in kind of all the this issue of time moving forwards or backwards or future, what's in the future, what's in the past. This is an equivalent way to state the Markov property, right? That usually it's somehow ignored, but it's very useful, right? So this is an if and only if statement, right? You see the double bars. This is really an if and only if statement, and you can try to show that given this, you then have this statement, which is the probability of x k is equal to little xk, conditioned on what happens in the future, only eventually depends, right, in the Markov kind of property way, on the closest point in the future, right? So this is xk plus 1 equals little xk plus 1, right? And everything else in the future is gone, right? It's irrelevant for a Markov chain. So intuitively this should make sense to you, but at the same time you kind of scratch your head and wonder, why do these imply each other, and does it have anything to do with reversibility or time reverse chains? And so certainly, as I said, this if and only if condition here does not only apply to time reversible chains. It applies to Markov chains in general. And so if you're looking for a challenge problem, you can try to see if you can work this out. And certainly it can be useful. And when you're solving problems, sometimes you really do need to condition on what happens in the future, right? And there, the Markov property can help you quite a bit as well. So definitely a useful thing to know about. And let's wrap up here.